name's Alex Jaeger. I'm a postdoc in electrical engineering in UCC, and I've been working on magnetic tracking technology, I think, since about 2014, 2015. So it's been about 5 or 6 years of me working in this space. And in this talk, what I'm going to do is introduce magnetic tracking as a concept, how it works, and then go into some details about some of the cool applications that you can do with this type of technology. And at the end of the talk, please feel free to fire away with any questions you might have. Hopefully I can answer them. So what is magnetic tracking? So to kind of summarize it into one sentence, it's real-time position and orientation tracking of discrete sensors using magnetic fields. So before we kind of go into the details of how it works on the physics level, let me just give you a quick demonstration. So this is a video here showing a tiny little magnetic sensor. It's about 0.5 millimeter in diameter. And what I'm doing here is I'm waving that sensor above what's called a magnetic field generator that's producing a time-varying magnetic field. And that sensor is picking up that signal. And the computer is then turning that signal into a position and orientation, that is X, Y, Z, and a set of angles. And you can see on the top right, there's the 3D computer screen showing the position in real time corresponding to my hand movements. So you may be wondering where this video was taken. This was in 2018 during the blizzard that we had in March. I brought my tracking system home with me from the lab and did some work in the kitchen. So that's why you can see the fridge in the background. But I managed to take a good photo at the time. So that's that kind of shows how the whole kind of technology works. So you can see in that video, we had a few different components. We had a sensor, which is that small little black strip that I had in my hand in that little red holder. On that flat piece on the table was the magnetic field generator. And just to the right, you would have seen a box with a cable. And that's what we call the control unit, or the base station. And so what happens is that base station sends a current signal to this field generator. That field generator produces a magnetic field, and that little sensor detects that magnetic field through induction. And that signal is sent back to the control unit, where it's measured and turned into a position and orientation. And the field generator is kind of cool. It's built from a printed circuit board. And what it does is that there are 8 discrete coils on there. And each of those coils is transmitting a low frequency magnetic signal in the kilohertz range. And each coil transmits a slightly different signal. So for instance, the first coil might transmit 2 kilohertz and the 8th coil might transmit 10 kilohertz. And you can set them up to transmit any frequency you want. And so what that provides by having these different frequencies being transmitted is you get what's called a spatially unique magnetic field, which means that for every point in space, the magnetic field at that point is unique. And based on that information, when the sensor is at some position in space, you can look at that signal, measure it, and then find out the position based on that measurement. So this video kind of shows what the signal on the sensor looks like. So each one of those coils I showed previously transmits a sinusoidal frequency in the kilohertz range. And all of those magnetic fields that are produced get mixed up in the volume above the field generator. So what the sensor sees as a signal is a kind of a sum of all of those sine waves kind of added together. So you can see on the scope here that signal is basically kind of a modulated sine wave. But when you actually take an FFT, or the Fourier transform of it, you can see these 8 purple peaks that appear. And each of those peaks corresponds to the frequency, or the magnitude of the frequency measured at that point. And so this is kind of a cool video showing how it changes with space. So you can see I'm kind of moving the sensor around the field generator. And you can see on the left, I have a live FFT, and that FFT is changing depending on where I move the sensor. So as I move the sensor further away, the signal gets weaker, and as I bring the sensor closer, you see the magnitudes of the peaks go up. And let's say, for instance, I'm above a particular coil, you'll see the particular frequency of that coil is the highest in the FFT. And so the way the position is calculated from those measurements is that we have a type of least squares minimization function in software that basically looks at the measurements from your sensor and compares it to a model of the magnetics. So we have some magnetic equations in software that simulate what the field is. At the same time, we're measuring the field in real life from the sensor, and then the computer tries to figure out what's the best fit X, Y, Z, and theta and phi, which is your orientation. What's the best fit of those coordinates to that model? And it does that by minimizing in software. And so the kind of key to all of these magnetic tracking systems are the sensors. And these sensors, as you saw in the first video, are really, really, really small. They're little coils, in fact. So it's a tiny little copper coil wound around a little ferromagnetic core. So that core is usually made out of, it can be made out of particular magnetic, ferromagnetic metal, or it can be made out of, I think new metal is one, ferrite is another. The ferrite can be quite brittle though. So different companies make different types of sensors, and you can see how small they get. So, you know, they range from about 0.5 millimeter wide to about 1 millimeter in their smallest designs, and about 8 millimeters long for the smallest one. And the ones that we use in our lab are the ones in the top left tile there, the 0.5 by 8 millimeters. And they're quite brittle, so you have to treat them carefully, but they work quite well, and they're really nice because you can put them into things. So if you want to track an object, you can stick a sensor to the object and track it that way. So this is a close-up of what one of those sensors look like. So what you're kind of looking at from left to right is about 8 millimeters of sensor. And so if we zoom in even further, and we got a company actually to take a slice of one of these sensors kind of vertically to see how they're actually made. And if you take the slice, you can see that there's thousands and thousands of these little, or maybe not thousands, but hundreds of turns wound around this this core. So this is magnified by 100, and if you magnify by 400, you can actually start to see the windings even better. I think there are 6 layers in this this winding, and I think based from their calculations, there's about 1,500 turns of copper on this sensor, which is crazy considering it's only 0.5 millimeter wide and 8 millimeters long. It's pretty extreme that they can fit that much metal or that many turns on such a small volume. And zooming out even further with an electron microscope, you can see that the actual diameter of the wire that's used to wind these coils is 25 micrometers. So that's about, I think it's about 1/3 to 1/4 of the width of a human hair. So winding these coils can be quite difficult. So we don't really do that in our lab in UCC. We buy these off the shelf because they're very specialized. So the fact that you can make these sensors so small makes them really useful for lots of different applications, because you can embed them into different devices. So a big application is in the medical space, and particularly in a procedure called bronchoscopy, where the doctor will investigate your lungs using an endoscope, which is like a thin, flexible tube with a camera on the end that he can use to kind of go through your trachea down into your lungs and see what's happening. So this is kind of the way cancer is diagnosed. Typically, they take a scan and then they use an endoscope to see where the cancer is. But as you can see, the lungs are really complicated. They kind of branch out and they get like a tree-like structure. They have kind of this root structure that it almost looks like a maze. Imagine trying to find where the cancer is and take a sample if you're if you're dealing with a structure that complicated. So companies like Medtronic have come up with a technology called Electromagnetic Navigation bronchoscopy, where essentially you put one of these magnetic sensors into the endoscope, and then combining the information from the sensor, the tracking position information, with a scan of the patient, you can create what's called a virtual bronchoscopy application, where basically the doctor can look at a screen like shown here, and basically the computer will tell them to turn left or right whilst they're investigating the patient's lungs. So yeah, it basically steers them towards the target. So it's a bit like a sat nav for your car, you know, it tells you where to go. The doctor will kind of click on the screen and say, okay, I want to go to this position in the lung, and then the software will give them directions saying to steer right or steer left as they go deeper into the airways. So it's really cool technology, and you can see in this picture the patient is lying on the field generator, that kind of white plate underneath the patient that's producing the magnetic field. And then the sensor that we talked about earlier is in the very tip of that device that he's using. So the kind of view that you get from using one of these systems is pretty cool. So from a first-person perspective, they take the scan from the patient, and then as the doctor is going into the lungs, on the computer screen they can see what you see here, which is kind of like a virtual perspective from the patient's scan. And basically it steers them towards the target. So the doctor kind of knows where to go, especially in these really, really narrow airways where sometimes a camera doesn't fit. And so sometimes technology like this is kind of the last resort to figure out where you need to go. So yeah, it's cool stuff. And this technology is getting better and better every year. Another cool application of tracking in general, not necessarily magnetic tracking right now, but optical tracking, is motion capture. So this is a cool clip I really like from The Hobbit, and it shows Benedict Cumberbatch doing the motion capture scene for the dragon Smaug, and you can see he's completely dotted all over with these little silver markers, and these silver markers are basically tracking. There's a camera nearby, and that's looking at Benedict, and it's tracking the position of each of those little markers, and it can basically find out where his limbs are and how his motion is, so they can capture that and animate the dragon. The problem is, as you can see, he's acting on his own here. Like in the film, he's talking to Bilbo, the Hobbit, but you can see Martin Freeman isn't in this clip. And the reason for that is because if he was in the clip and he was acting with Benedict, he might be blocking the camera, and that would break the whole motion capture setup. So kind of in this kind of area of optical tracking and magnetic tracking would make a great alternative, because it would allow the actor to actually act with their fellow actors and make their job a bit easier. So this is an application now where instead of optical, they use magnetic tracking, and it's a cool application for kind of monitoring the position of a guitarist's fingers whilst he's playing. And you can see on these fingers he has about, I think it's about 12 or 13 magnetic sensors in total. And you can see on the right on the computer, you can see the really intricate movements of his fingers are being captured. And you can see he has to curl his fingers quite a lot when he's playing the guitar. And if those sensors weren't magnetic, if they were optical, there might be a position of his finger that cannot be captured by the camera. And so the motion capture would break. But in this case, because he's using magnetic tracking, it doesn't matter where his fingers are, it can always be captured. And your experiment will not fail if somebody walks nearby or whatever, or he puts his fingers into a weird position to play a particular chord. So that's one application, or a second application. Another upcoming application is virtual reality. So kind of linked to the motion capture with the optical system, VR operates in much the same way. You have these cameras, or lighthouses as they're called, in your room, in your sitting room, and they look at your headset to basically see where you are in space so that they can map your movements into the game successfully. But as you've noticed so far, all virtual reality games are single player. Very few multiplayer games out there that aren't online. You know, you can't have two people in the room doing VR simultaneously unless you have quite a complicated setup. Because one person might block the other person's view from the point of view of the tracking camera. So for the moment, VR is single player only. But if they were using magnetic tracking, that wouldn't be the case. And there's a lot of work going into this. People are building transmit coils or the field generator coils into the actual headsets, such as like the Oculus Rift, for instance. I think the guys there's some research going on where they embed the field generator coils into the headset so that they can basically track the movements of the person, of their hands or whatever, relative to the head. And that doesn't require any cameras anymore, which is quite clever. And in our lab as well, we have students, especially Marco and Charu, are working on updating on the magnetic tracking system technology, particularly on the area of wireless tracking. So making a tracking system that doesn't have wires, because as you've seen earlier, all the magnetic sensors so far have had cables attached to them. And that's a big advantage of optical, is that you don't have wires, but with magnetic you do. So if you could combine magnetic tracking with something like Bluetooth, you could create a fully wireless motion capture system without the negative of potentially being blocked by another user nearby blocking the camera. So this is quite a funny picture I found of somebody modifying an Oculus Rift with a bunch of magnetic coils. It looks absolutely daft, but I thought it was kind of cool to finish up the talk. So yeah, thanks very much. And please, if you have any questions, please fire.
Well, first of all, thanks so much for the talk. Absolutely interesting technology. Maybe one question would be, is there a difference having all the coils in a plane versus having them angled like in this picture?
Yeah, there is a difference. So let me go back there now to where was it at the beginning? Well, this will do. So I suppose our initial reason for going flat and planar was because the cost was very low to make a PCB. Like, this is a 2-layer circuit board, so the end result is that you can make something that's very low cost. I think each of these boards cost about $10 or $12 to make. But the disadvantage comes from a tracking point of view. So especially when it comes to tracking with distance. So the problem is you have all of these coils, because they're flat, they're all kind of pointing in the same direction. And so that's one of the reasons why we need 8 coils. It's because because they're all in the same plane, you lose some information in your magnetic fields. You can get away with less coils. For instance, some people do use 5 coils instead of 8, but in those systems, the coils are tilted at an angle. And to tilt a coil at an angle, you can't use PCBs anymore, especially if you want every coil to be at a different angle. So you have to resort to wound coils then. So you have to basically wind them on a spool, which you can buy off the shelf, like inductors or coils of wire to do that. Or you can get them custom wound yourself, which is a lot more expensive. So yeah, they're the kind of 2 main approaches. But I think the planar ones are also very nice. I forgot to mention, especially in the medical application. So the fact that if something is flat, it means somebody can actually lie down on it without it, obstructing their movement or their comfort too much. But yeah, those are kind of the main reasons.
Alex, Perfect presentation. That is great. I do have a question about actually the resolution of your system. Well, I could see from the coils that they're a little bit apart from each other. So what I mean, I've noticed also that the FFT amplitude is changing when you're changing the secondary coil over the first or primary coil. Yeah, exactly. That's very good actually. So have you did you have a chance to test what was the minimum distance that you could move your secondary coil and your system was able to detect that minimum? Because the reason I'm asking is in those surgeries application that you've shown, the minimum movement is very important, because if you, for example, sometimes if you move a needle or something like that just a millimeter wrong, then you might cut a very sensitive nerve or something like that. So have you did you get a chance to test or measure the minimum detectable movement that your device or your 8 coils can detect, and is increasing the number of coils and decreasing the size of them, will the decreasing the size of them and increasing the numbers, will that help with increasing the sensitivity of the movement?
So to address the first part, which is the minimum kind of resolution or the minimum movement that can be detected,
it
is extremely small. You can of course it depends on what height you're currently at above the field generator. But for instance, in the pose that that I am at in this video here, I'm about, I think, 5 or 6 centimeters. Okay, now I go up to like 30, but initially when I was going side to side, I was about 6 or 7 centimeters above the surface. And there you can get to like hundreds of microns level of precision. So I about like at that height, I would estimate, back from when I did the experiments, it was about maybe 300 to 400 micron of a resolution. Now, the higher you get above the field generator, of course, the noise starts to dominate a bit. So you have to kind of average that bit more. And so, for a given set of sampling settings, your resolution will go down the further away from the field generator you go. But in the kind of prime operating condition, I'd say between 300 and 400 micron would be typical minimum detectable. And that's an X, Y, and Z. Now, if you're talking about orientation, that's a completely different ballgame, because the magnetic field is detected along the axis of that sensor, so kind of in the longitudinal axis. So because of the way trigonometry functions work, a tiny change in the angle can cause a massive change in the received field. So the angular accuracy is less than like 0.1 degree. In its optimal operating range. So
I see.
And sorry, just to address the second part of your question then, which was more coils but smaller. Yes, that will help the accuracy in some ways, because a lot of the resolution of these systems comes from not just the strength of the field, but how much it's varying in space. So as you move the sensor from left to right, by how much is the field changing as I'm doing that? And so by having a smaller coil, but more of them, you're kind of introducing bigger, how you'd say, gradients, spatial gradients of the field with movement. And so, yes, your accuracy would go up, but because you have so many more coils, your software gets much more complicated from a computational burden point of view. So that's the trade-off, of course.
That's true. That's true. Okay, thank you. That was great.
Actually, Alex, random question from the slide. You know, when you move the coil, your noise floor like close to the peaks rises, is that like the Doppler shift or something? Or what's causing the spectral leakage?
Well, you see, it's interesting because I think in this, this, how should I say, in this setup, I think I'm capturing about 2,500 samples per FFT. And I think the sampling rate is about 100 kilohertz. And you see what's happening as I'm moving that sensor is it's moving during the acquisition of those samples. So what's actually happening is that as I'm moving the sensor, I'm modulating those sine waves with my movement. And that modulation causes, I think, sidebands. And those sidebands don't correspond to the bin of the FFT. And that causes the leakage. So that's why you'll see when the sensor is completely still, there's no leakage whatsoever. But then the moment I move it, there's some sideband effects, and that causes the leakage. So
that's good. I wonder if you could use the sidebands as like a velocity measurement to like confirm, oh, I've moved X 1 millimeter by the velocity of this per second. I don't know.
Yeah, we've looked at that. The trick that it becomes difficult though when you're like it's fairly easy to see when you're quite close to the field generator and your magnitudes are very strong. But once you get a bit further away, like you see now, that leakage is below the noise floor, so you can't measure anymore. So your velocity measurement doesn't work then. But we've had a look at it before, and it works quite well actually when you're up close. But when you're far away, the leakage doesn't work anymore.
That's good. What kind of calibration was required for this? Like in general, I suppose, not really specifically.
I suppose like the biggest calibration hurdle is kind of trying to I suppose if we go back to I tried to keep the maths in this presentation to a minimum, but we have one equation. So you can see we have this we have our sensor measurements here on the left, and we have our model on the right. But you can see we have this kind of kappa, this K here on the left side beside the sensor measurements, and that's basically our calibration. And so our model basically assumes a perfect situation. It assumes like there's like 1 amp of current flowing through the coils, and that the sensitivity of our sensor is a factor of 1. And it assumes everything is unity. But of course, in real life, when you have amplifiers and filters and gain stages, the signal that you receive from your physical sensor will not match that model at all. So what we have to do is calibrate the system to obtain a set of scalars that essentially map our measurements to the ideal model. And then once you have that, this whole equation works just fine, and you can solve your positions from measurements. So that process of calibration requires you taking basically position or measurements of the sensor in known positions, like for instance a mechanical fixture, and then because you know those measurements, you can then infer what the calibration is, and back from that, and then you can then track freely from then on in any position. So does that answer your question?
Yeah, no, thanks. Yeah, no, that makes sense. Thank you.
Alex, thank you for a great talk. It's amazing to see how the same technology can apply to so many different applications, from surgery, medical applications, to virtual reality and games. If there is any other question, otherwise we let Alex go. That did a great job.
Yeah, and I don't know if it interests anybody, but my email is there on the bottom. So yeah, I don't know if you have questions or ideas or whatever, you want to find out more, shoot me an email and I'd be happy to have a chat. So.
And possibly, Alex, I think also opportunities for a thesis or for a postgraduate position. I don't know, but maybe if someone is interested to do some 6-month thesis job, the contact.
Yeah, I don't like, I'm a postdoc, but I don't I don't have my own pot of money or pot of funding, so I'll have to talk to my boss before that happens. But yeah, it's a very good idea. I should.
Anyways, any further question that you may have, you can contact Alex.